On paper, Oklahoma is a century old. Born in 1907, the 46th state in the United States lies near the center of that area of dry land known as the North American continent and comprises almost 70,000 square miles of stone, water, and soil. The story of Oklahoma's landscape begins long before the arrival of the first human inhabitants. From rock outcrops, drill holes, and seismic waves, geologists have interpreted from Oklahoma's rocks that the land probably formed over a long time. This period of time, known as the geologic timescale, is currently estimated at over 4.6 billion years in length. The geologic timescale can be broken down into major parts, or eras, and those eras are further subdivided into periods, which may be millions of years in length.
Hi, I'm Devin Denny. Join me today as we unlock the secrets in Oklahoma's rivers, soils, and stone.
There are three basic types of rocks in Oklahoma. Igneous rocks are the most primitive rocks on Earth, as they formed from the cooling of hot, molten material. Sedimentary rocks are very common and may include limestones, shales, or sandstones that formed from sediments or biological activity. Metamorphic rocks are more rare and form due to changes in igneous or sedimentary rocks from heat or high pressure. Oklahoma's oldest exposed rocks can be found today in the Arbuckle Mountains, a low-lying chain of hills in south-central Oklahoma. Radioactive isotopes in these rocks suggest that these rocks formed 1.4 billion years ago, during a time the scientists call the Precambrian. Precambrian is the time between the formation of the Earth and the formation of the first complex life forms. During the time when these first rocks were cooling from hot, molten magma, only the most primitive of single-celled organisms existed, such as algae or primitive bacteria. Geoscientists come to quarries like this one, near Troy, Oklahoma, to study these oldest of Oklahoma stones. Today, shallow mines harvest the igneous and metamorphic rocks out of these ancient deposits for use as construction material. In fact, the stone from this area was used in the construction of the Oklahoma State Capitol building. One of the largest outcrops of Precambrian granite in the state is found near Troy at 10 Acre Rock. The story of this barren, granite landscape for the next 800 million years is mostly unknown, but the barren lands, devoid of any land plants, were ground flat by erosion over the next 800 million years. With the approach of the shallow Cambrian Sea, new complex life had begun to form, and the Paleozoic era of Earth history had begun.
One household food will give you a fairly rough approximation of what the inside of the Earth looks like, and that is the ubiquitous avocado. If you take the avocado and you cut it down the center, so the avocado has a fairly rough approximation of the Earth. The avocado, much like the Earth, contains several different layers, and it's a very approximate model for the way the Earth is structured. Unlike the Earth, the avocado seed is the core of the avocado. The Earth's core contains two layers, a liquid outer core and a solid inner core of iron and nickel. This generates the Earth's magnetic field. In the avocado, the green, pulpy, fleshy portion of the fruit is roughly the same dimension and thickness as the mantle, which is the second to layer from the top in the Earth. It's considerably thick and is contained of a very high pressure, high density rock. There is a transition zone here in sort of a dark green between the pulpy flesh and the skin. In this case, in the Earth's crust to mantle, we also have a transition zone called the asthenosphere. And the greenish skin on this obviously is very thin compared to the entire avocado, and much like the Earth, this is a very thin crust floating on a very vast volume of rock in the mantle. So that's a fairly decent approximation for the Earth, given a slightly smaller avocado seed. This is a pretty good size one, actually.
Well, what we had here in those, say 600 million years ago, we had what was called Laurentia, was the name of this continental mass that we now call North America. And the crust in this part of North America was around 1,400 million years old.
The continent of Laurentia is the original continent that the most of Oklahoma started as, and it formed millions and millions of years ago, hundreds of millions of years ago. The continents make up about 1/3 of the Earth's surface, with the other 2/3 being oceanic crust.
In the latest Precambrian, which would be this sort of 540 million years old and older, this would have been basically a rather low relief plain of igneous and metamorphic rocks at the Earth's surface. There would have been probably not too much soil. There would have been some, but not too much. There would be no land animals. As far as we know, no land plants. It would be a very barren landscape.
Scientists have recently discovered that the Earth's crust is actually broken up into a set of distinct units, or plates. And each plate fits together like a jigsaw puzzle, each moving independently around the Earth's surface. There are three main types of plate boundaries. The red lines on this map show extensional or divergent boundaries where rocks are pulling apart. Yellow lines on this map show areas where plates are coming together in compressional or convergent plate boundaries. And the dashed lines represent transform boundaries where the rocks are sliding past each other. In plate tectonics, whenever two plates that are together then move apart, we call that a divergent plate boundary. And at a divergent plate boundary, the landform we most typically get is called a rift.
During the time around 550 million years ago, plate movements, or mantle hotspots, created a rift, or weakness in Earth's crust, allowing magma to rise up and form igneous rocks like gabbros, rhyolites, and granites.
As Earth's mantle shifts around and the pressure comes off, different minerals that are less dense sort of float to the top. And as the pressure comes off, they bubble up and form magmas. And those magmas can have many different crystallizations for many different reasons. But the lighter components form granites, and those granites form the basis for our continents.
And around the period somewhere around 550 million years, the crust started to break apart here. And a huge chunk of what would have been Laurentia, the part of all of northeast Texas and probably northern part of Louisiana, moved off by plate tectonic processes and is now found in Argentina.
During this rifting, several types of igneous rocks were formed. Igneous rocks may cool slowly deep beneath the Earth's surface, creating rocks such as granite or gabbro. Other times, rocks erupt quickly to the Earth's surface, creating fine-grained rocks such as rhyolites or basalt. The chemical composition of the molten rock dictates in large part what type of rock forms after cooling. These rocks are found today in the Wichita Mountains because of their unique geologic history.
When you have the crust of the Earth pulled apart this way, what it allows is the hotter mantle to come up underneath closer to the surface. And in that process, melting goes on. What really melts out first is basalt, mafic rocks. Because that liquid is more buoyant, it rises up toward the Earth's surface, and this is rising up inside this rift. Well, in the process of bringing this basalt up, several different things can happen. Sometimes you can melt what pieces of the existing crust are there, or in the process of crystallizing the basalt itself, you can, by fractional crystallization, in effect end up with very silicic things like granites and rhyolites.
One thing that you can do at home to really get an idea of how the crust and the Earth's mantle work together to create a rift in the Earth is to take a toaster pastry, put it in the oven and warm it slightly. And what we're going to do is take our thumbs and put it underneath and slowly press upward. The pressing upward is the hot mantle pushing upward against the crust, and the convection of the crust pushing the two halves apart. So the mantle is heating, it's pushing up on the rift, which is in the center of the toaster pastry. I'm getting extension along the edges, okay, because the cool areas away from the rift are pulling away. So what I'm getting is an upwelling, and you see that the cracks in the rift start to form. In this case, here's a triple junction where 3 rifts come together. If I continue that pressure, 2 of those will activate, 1 of them will fail. Okay, and in this case, on my left hand, I pulled a little too hard, and now the rift is formed on my left hand. We have active extension going on here, and now we have a failed rift here. This is the triple junction. This side and this side are 2 arms of the rift that are now active. So this is an exact model of the Oklahoma rift. This is a failed rift. North America is here, the rift is here, and this little hole on a global scale would have been where thousands and thousands of feet of sediment filled in an ocean during Cambrian and Ordovician time.
The results of millions of years of geologic activity make this part of a must-see area for an Oklahoma road trip.
Wichita Mountains National Wildlife Refuge sits just northwest of the town of Lawton, Oklahoma. It was the first U.S. game and wildlife preserve set aside in 1901 by then President Teddy Roosevelt.
So this is an interesting place where you can see these rift-related rocks being exposed.
The refuge's unique geologic features provide a home to hundreds of native Oklahoma wildlife.
All the tiny crevices and the large boulders provide wonderful habitat for reptiles and amphibians out here. There's about 55 different types of reptiles altogether: turtles, snakes, lizards.
Well, everybody, when they come, they're going to look for the buffalo, and most of the time they're going to see the buffalo. And west of the visitor center, where we have a big prairie dog town.
This prairie dog town comes with its own geologic landscaping, large black boulders of gabbro. This gabbro, the oldest igneous rock in the Wichitas, is an iron and magnesium-rich rock that formed deep within the earth and served as a geologic foundation for the area, for the deposition of rhyolite and granite.
We're on a particular granite called the Mount Scott granite. It's an interesting granite. It's named for Mount Scott itself. And it's a tabular sheet, or once was a tabular sheet, that was on the order of 50 kilometers long by only about a half a kilometer thick, and probably 15, 20 kilometers wide. So you have kind of like a big pancake of silicic liquid that was intruded right on top of a previously crystallized gabbro and under a cover, shallow cover of rhyolite that had come out earlier. So you got this sequence of gabbro on the bottom, granite, and then rhyolite.
Geologists might consider the Earth their oyster. I, on the other hand, consider the Earth my nice chocolate cake. So this cake, if we assume it represents the Earth, is similar in that if we take a cut through the middle and pie slice the thing open, what we see are many different layers. This is typical of what geologists see in the rock record. Much like the Earth, a cake is formed from the bottom up. We put down the bottom layer first, the next layer second, the third layer third, and so on. And the layer on top and the icing is the last thing to go on. We call that in geology relative age dating. It gives us a way to understand the sequence of events that occurred in the rock record. In the case of the Wichita Mountains, there are many different layers of igneous rock. We've got a bottom layer of gabbro, which might be, say this dark material in here. And then on top of that, we overlay a rhyolite, which let's say is this lighter material in here. What's interesting about the Wichita Mountains is a younger rock, in this case, the Mount Scott granite, came in later and sort of intruded its way in between the two layers, doming them up. So, in this case, the rock in the middle is actually a little younger. Geologists have to very carefully work out the sequence of events in order to tell that this stuff in here is younger than the stuff above or below it.
As we look at the mountains today, we see the rhyolite has been eroded away over time, and very little remains exposed in the Wichitas. The contact between the pink and red granite and the black gabbro can be easily seen from the highest point in the park, Mount Scott.
At Mount Scott, visitors can take a drive up to the top of the highest peak in the range in order to get an impressive view of the entire mountain chain. From there you can see how sedimentary rock, which is weaker and softer than the igneous rocks of the range, is slowly being eroded away, uncovering this ancient land.
If we're looking for those kinds of contacts just regionally, usually there's much more vegetation and trees on the gabbro because it's a different chemical composition than on the granites or on the rhyolites.
The Mount Scott granite is the most commonly encountered rock by park visitors, but with a sharp eye out, visitors may also see a rock more common on the volcanoes of Hawaii, dark-colored basalt.
Now we have basaltic dikes like this scattered throughout the Wichitas, and what this really helps us show is that even the youngest granites we have some basaltic dikes cutting them.
The mixture of dark basaltic igneous dikes and the light-colored silica-rich rocks, such as granite, help geologists work out the sequence of events that reflect the beginnings of Oklahoma's stony foundation. Following the rifting and volcanism of southern Oklahoma, the land level began to subside with the load of the new cool and dense igneous rocks. During this time, the shallow seas crept in and covered the barren landscape. Sediment eroding off of the igneous plain collected in the new shallow sea, forming the first sedimentary rocks in Oklahoma. This basal sandstone, called the Reagan sandstone, is found in the Arbuckle Mountains. Soon the shallow seas covered the region, at first intermittently, between islands of igneous rock, forming the varied Timbered Hills group carbonates. As the land slowly subsided, limestones and dolomites formed, building upward into great thicknesses throughout latest Cambrian and early Ordovician time. These early marine rocks of the Timbered Hills group can be seen today exposed in the westernmost Arbuckle Mountains. This area, aptly named the Slick Hills, is made up of shallow marine rocks of limestone and dolomite that originally covered the Wichita Mountains rocks, but have since been eroded away and are now confined to its northern slopes. The area is named for its relatively treeless hills and featureless outcrops. Today, the exposed topography of the Slick Hills is prime territory for capturing the ceaseless Oklahoma winds using modern wind turbines.
It's a place where the ocean tried to split apart and form basically would have split Oklahoma in half as we know it today, but it didn't make it very far. What happened is it started to split apart and then it filled up with volcanic rocks. Those volcanic rocks cooled, and when things cool they sink, and that produced a deep basin which then filled up with sediment and that's where all these carbonates formed.
In early Ordovician time, massive thicknesses of rock formed throughout the new basin. This group of limestones and dolomites is called the Arbuckle group, which formed the bulk of the Arbuckle Mountain chain rocks. A large outcrop of these rocks can be seen along I-35, north of Ardmore, Oklahoma. The Arbuckle group forms a unique landscape called tombstone topography. During this long, continuous record of Earth's history, we find a rapid diversification of marine invertebrate creatures was occurring throughout Oklahoma. As life was diversifying, more and more marine organisms were creating new rock. These include strange but fascinating organisms like the trilobite. Next time, we'll take a closer look at early life and mountain building in Oklahoma.